Diekmann condensation is the intramolecular condensation of esters to give beta-keto esters with the formation of a ring. In this video, we're going to talk about the reaction conditions and its mechanism. So let's begin. Right, so Diekmann condensation is actually a modification of the Claisen condensation. We have already discussed Claisen condensation in a previous video, the link to which you can find here. And if you remember, in Claisen condensation, two ester molecules condense together, which means that is an intermolecular condensation of esters to give beta-keto esters. While in Diekmann condensation, the two ester moieties are present in the same molecule. So it's an intramolecular condensation of esters to give a beta-keto ester. But the difference in the products in both the reactions is that Claisen condensation leads to the formation of an open chain molecule, while a cyclic structure is obtained in Diekmann condensation. Let's see how the ring forms through its mechanism. So we have this beta-keto ester, and it is treated with a base. And now you know that base can abstract any acidic protons. So we have two sites here. These alpha protons, they are acidic, and so are these alpha protons next to the carbonyl. So any of these four protons may be abstracted by the base to form an enolate. Now what happens as a result is that when this enolate collapses back, these pi electrons, they attack the second carbonyl group that is present in the same molecule, and again an oxyanion is produced, which when collapses back removes this alkoxide anion. And now you can see that a bond is formed between this carbon and the carbonyl carbon. Right, so what we have now is a 1, 2, 3, 4, 5 membered ring in which we have this ketone, which is restored. The ester has been converted into ketone because of the removal of this alkoxide anion, and this ester group is restored, and because it is attached to this carbon, which is now part of the ring, this one next to the carbonyl, so we draw it here in this form. So you would think that the reaction is over, but because we have this alkoxide anion in the system, now it has been released in the previous step, so it can easily remove this acidic proton, which can lead to the formation of another enolate like this, with the removal of this alcohol molecule. This enolate anion is then treated with an acid. Acidic workup is carried out in the second step, as you can see here. So this enolate collapses back and it takes this proton to restore the ketone moiety. So a 5-membered ring is formed as a result. Now you already know the feasibility of the formation of 5 and 6-membered rings. So Diekmann condensation usually gives these two types of rings because they are easily formed owing to less ring strain. And you can see here that we have this example here. It's a 1, 2, 3, 4, 5, 6. It's a 1,6 diester, which leads to the formation of a 5-membered ring. But if we have a 1,7 diester, that will lead to the formation of a 6-membered ring. This will be the final product. You can try it for yourself following this mechanism, how this 6-membered ring will be formed from a 1,7 diester. So this is all about Diekmann condensation. Stay tuned for more named organic reactions in the upcoming videos. Thank you so much for now.